The mysterious signal GPM J1839-10. Could it be from an extraterrestrial civilization? On our planet, two critical observatories help us observe any radio signal from space in the Earth's two hemispheres, the North and the South. These two observatories are the Very Large Array, abbreviated as VLA, located in New Mexico, and the Murchison Widefield Array, abbreviated as MWA, in Australia. Both observatories have enormous radio antennas and radio telescopes distributed in extensive desert fields. These radio telescopes are strategically located in those areas of the world to capture signals in both hemispheres of our planet with better precision, since they are susceptible to radio waves from other stars and distant galaxies. But recently, scientists working at the VLA and MWA published an article describing a surprising radio source that reaches Earth every 22 minutes and whose nature is still unknown. This signal, classified as GPM J1839-10, is unique and remains one of the most recent mysteries of astronomy. So what is this signal that repeats every 22 minutes? Could it come from an intelligent extraterrestrial race trying to communicate with us? Join us on this journey of knowledge to find out. It arrived on Earth 35 years ago. To understand the source of radiation, scientists decided to check if something similar had been recorded before in this area of the sky. And they were surprised to find the same signal at the same point in the recordings made in 2018. That's when they assumed that something exciting and unknown was producing that pulsating signal. Furthermore, when scientists checked the recordings made with the Very Large Array, they found the GPM J1839-10 signal in recordings made in 1988, when this radio telescope was just beginning to operate. This means that the human race has been capturing this signal for more than 30 years. But because it has been such a long period, they had not paid attention to it until now. What object can produce signals like this? Seeing that it was a pulsating signal with an exact and repetitive frequency, astronomers immediately thought of the only object in the universe capable of emitting that type of signal: a pulsar. A pulsar is a rapidly rotating and highly magnetized neutron star. The formation of pulsars is intrinsically linked to the life and death of massive stars. It begins with the existence of a massive star several times larger than our own Sun, which has exhausted its nuclear fuel. When these types of stars reach the end of their lives, they face catastrophic gravitational collapses, forming highly dense objects popularly known as neutron stars. During the death of a massive star, matter is compressed to extreme densities. In this process, electrons and protons combine to form neutrons, giving rise to a neutron star with an incredibly dense and highly magnetized core. A neutron star is the heaviest object in the universe, only after black holes. This type of star can have the Sun's mass compacted into a radius of a couple of kilometers. Because of this, the mass of a neutron star is so great that if we could take a single tablespoon of material from a neutron star, that simple tablespoon would weigh more than Mount Everest. Neutron stars created under certain conditions in which the angular momentum of their rotation is conserved can lead to very rapid rotation. This process can generate an intense magnetic field, billions of times more potent than the Earth's magnetic field. And the combination of rapid rotation and a powerful magnetic field will eventually cause the neutron star to begin spinning very quickly. Neutron stars can spin several hundred times per second. A point on its surface may be moving at speeds of up to 70,000 kilometers per second. Neutron stars that rotate so quickly expand at their equator due to this dizzying speed. This also implies that these stars have a size of a few thousand meters, between 10 and 20 kilometers, since the centrifugal force generated at this speed is enormous, and only the powerful gravitational field of one of these stars can prevent it from breaking into 1,000 pieces. On the other hand, neutron stars give rise to one of the objects astronomers imagined when they saw the signal received at the VLA and the MWA, the pulsar. A pulsar is a rapidly rotating neutron star that emits beams of electromagnetic radiation. This radiation is emitted in the form of regular pulses detected by telescopes on Earth. The frequency of these pulses is typically in the range of radio waves, although some pulsars also emit at other wavelengths such as X-rays and gamma rays. The exact mechanism that gives rise to the emission of these pulses is related to the inclination of the neutron star's rotation axis and the associated magnetic field. Radiation beams can sweep through space like a lighthouse if these two axes are not aligned. When one of these beams is pointed towards Earth, it is detected as a pulse of intermittent light that appears and disappears with an easily recognizable frequency and period. The rotation speed of pulsars is astonishing. Some pulsars can rotate several times per second, reaching extreme angular speeds. This rapid rotation phenomena is due to the conservation of angular momentum during stellar collapse. In addition to their impressive pulse emission capabilities, pulsars are notable for their temporal stability. The regularity of the pulses is so precise that it has been used to measure with extraordinary precision phenomena such as the expansion of the universe and the presence of massive objects in its vicinity. Observing and studying pulsars have provided astronomers with a unique tool to explore various aspects of the cosmos for years. Some of the most notable contributions include the experimental verification of certain aspects of Einstein's theory of general relativity, the detection of planets orbiting pulsars, and understanding of the density of interstellar matter. Additionally, pulsars have been instrumental in exploring magnetic field dynamics in extreme astrophysical environments. These objects provide a unique window to probe the extreme conditions found in the cores of neutron stars. Pulsars are neutron stars that rotate on themselves at high speed and emit beams of radiation that can be seen from Earth as light pulses. Does this mean that the GPM J1839-10 signal is a pulsar? Well, at first it was thought that a pulsar was the astronomical object that best described the GPM J1839-10 signal, but there was a big problem. The rapid rotation of pulsars is due to the principle of conservation of angular momentum during the gravitational collapse of a massive star into a neutron star. When a massive star exhausts its nuclear fuel and reaches the end of its life, it experiences a gravitational collapse. This collapse compresses the star's matter to extremely high densities, forming a neutron star. During this process, the initially rotating star contracts, and according to the principle of conservation of angular momentum, its rotation speed increases as its size decreases. Angular momentum is a physical property associated with the rotation of an object and is conserved in closed systems without the application of an external torque. Simply put, if an object is rotating and no external forces are acting on it, its rotation speed will increase as its size decreases. The problem is that pulsars cannot rotate slowly by their very nature. There is no minimum speed at which a pulsar can spin, but usually they can spin hundreds of times per second. It is physically impossible for a pulsar to spin as slowly as the GPM J1839-10 signal. In other words, it is physically impossible for the GPM J1839-10 signal to be a pulsar since it rotates too slowly. But if that is so, then the initial question arises again: what object produces this mysterious signal? Before moving on, be sure to like or dislike the video so that we can improve them for you, the viewer. Plus, don't forget to subscribe to our channel by making sure to hit the notification bell so you don't miss any of our daily videos. Magnetar. A magnetar is a type of neutron star with an extremely intense magnetic field, among the strongest observed in the universe. A highly magnetic magnetar is among the cosmos' most energetic and exotic forms of matter. Like a neutron star, the formation of a magnetar is linked to the supernova explosion. This cataclysmic event occurs when a massive star exhausts its nuclear fuel and collapses under its gravity, dying in the process. During the collapse or death of a massive star, the star expels its outer layers, and the remaining core collapses to form a neutron star. In the case of magnetars, it is believed that the original magnetic field of the massive star is significantly amplified during this process. The physics behind the phenomena observed in a magnetar is complex and not yet fully understood. However, there are several proposed theories and processes that explain some of the notable features of these objects. Magnetic dynamics. A magnetar's powerful magnetic field plays a crucial role in its behavior. It is thought that the magnetar works like a giant magnet, interacting with the surrounding matter and generating intense magnetic phenomena that do not exist in our solar system. Magnetic storms. Magnetars are believed to experience occasional magnetic storms, during which their magnetic field undergoes drastic changes. These events can give rise to intense radiation emissions at various wavelengths, including X-rays and gamma rays. Remember this very well, which is crucial to understanding the GPM J1839-10 signal. Gamma ray emission. Magnetars are sources of gamma ray emission, the most energetic photons in the electromagnetic spectrum. This emission is related to intense magnetic activity on its surface. Bursts and soft bursts. In some cases, magnetars have been associated with gamma ray bursts, highly energetic events that release large amounts of energy in short periods. Soft bursts have also been observed, less intense but more frequent emissions. Thanks to understanding magnetars, some scientists speculate that the GPM J1839-10 signal could simply be a magnetar with a magnetic storm occurring on its surface for 22 minutes. But other scientists do not think the same. The main reason is that stellar earthquakes that occur on the surface of stars are temporary phenomena that could in no way extend indefinitely for more than 30 years. If the GPM J1839-10 signal were a magnetar, we would have seen the signal a couple of times and then it had dissipated. But the fact that it had been there for more than 30 years indicates that there is no way it can be a magnetar. So what could this mysterious signal be? Highly magnetic white dwarf. Another option is that this signal could be a white dwarf with an unusual magnetic field. White dwarfs are the remnant of a star the size of our sun that died and left a remnant of the core, which is now compacted. A white dwarf star can produce radio emissions similar to those observed with the signal, and since it is not a neutron star, it could rotate a little slower, perhaps at 22 minutes, corresponding to the GPM signal J1839-10. The problem with this is that to fit the models to white dwarfs, they do not have a powerful magnetic field like pulsars. In fact, as of the creation of this video, ARSCO is the only known radio pulsar that is a white dwarf. Its radio emissions are approximately 1,000 times less luminous than the GPM source J1839-10. So far, none of our models or scientific theories fit what the GPM J1839-10 signal could be. Also, the current understanding of neutron stars is that below a certain rotation speed, called the death line, their emissions cease. Uniquely, GPM J1839-10 not only has an extremely low rotation of approximately 22 minutes, but also emits bursts of radio waves lasting up to 5 minutes, for which there is currently no generally valid scientific explanation. Even some scientists do not rule out the unrealistic but possible idea that it is an unmistakable signal placed there by an extraterrestrial civilization much more advanced than us. Now it's your turn. We want your thoughts. So tell us, what do you think the 22-minute signal GPM J1839-10 is? Let us know your opinion in the comments.